we can start. So good afternoon, everyone. Welcome to the third lecture by Laure Gouba on Green's functions. And I don't need to introduce Laure again. You already met her a few times. So Laura, without wasting any of your precious lecturing time, you're welcome to start sharing your tablet or whatever you're using to write. And I just quickly remind the participants, please, to use the Q&A or raise your hands. We are not so many, so I can easily give you the right to talk if some critical questions needs immediate answer. Yeah. So Laura, please, over to you.
Okay, thank you very much, Professor Petruccioni. And good morning for those that just wake up, and and good afternoon, everyone. So it's a pleasure for me to continue with this session of mini courses of October. Started already 2 weeks ago. Today is the third session, and I would like first to remind you about the last two first session that is considered as introductory, and that are very important to be reminded for what we'll be doing today. So let me go. No, I close. I'm looking for the full screen view, but it seems not to be fine. Okay, so Bo, let's continue. So today we are at the third session, and if the title for the mini course is Green Function for Ordinary Differential Equation. And on the first session on 5 of October, I talked about generalities, about second order. Okay, let me, okay, let me see. Thank you, Van Zyl, for the advice. Let me see if I get full screen. Okay. No. Usually I took full screen. Okay, it's fine here now. Okay, right.
Perfect.
Thank you. So then for the second session on the 12th of October, that was last week, I introduced the integral operator and differential operator in the sense that I will be using today. And the today's session is about green functions. I will define the green function, then I will give the properties, but I will not give demonstration of the properties because you can find it in the reference book of Philippe Denery and collaborator. And then how one concretely construct a green function. And then next week, what we'll do is to take an example that we solve concretely, because also what I've been saying up to now are more abstract. So let's see the summary of session 1. So session 1, it was important for me to introduce to you a non-homogeneous second order linear differential equation. That is an equation of the form AX, the second derivative of u with respect to x, is first bx times first derivative of u with respect to x, and cx times u, that is equal to function f of x. And then in a most general form, the coefficient A of x, B, x, C, x are complex value. But here I consider that it's a real value for that reason. If it's second order, A of x is different from 0 and x belong to an interval A, B. Here it's non-homogeneous because my non-homogeneous term is f of x that is different from 0. And to this equation is associated boundary conditions. And most of the time there are two boundary conditions I said 2 weeks ago. That is a form, I call it B1 and B2. Then for a non-homogeneous second order linear differential equation, there is always what we call the associated homogeneous equation. That is the same equation, but just that for homogeneous equation, f of x is equal to 0. And then boundary condition are also considered as it is for the non-homogeneous case. Then a homogeneous equation admits two linear independent solutions, and if two linear independent solutions of a homogeneous equation are found, these two solutions are called a fundamental set of solution of the homogeneous equation. And because of the linearity of the homogeneous equation, a linear combination of the fundamental set of solution is also a solution of the homogeneous equation. Then theorem 1 that says that the most general solution of the homogeneous second order linear differential equation is of the form u of x is c1 u1 x plus c2 u2 x, where c1, c2 are arbitrary complex constant, and u1 x, u2 x are the fundamental set of solution. Then the second theorem that I've given 2 weeks ago is that the most general solution of the second order non-homogeneous differential equation is of the form ux is c1 u1 x plus c2 u2 x plus upx, and up is any particular solution of the non-homogeneous equation, and u1 u2 are a fundamental set of solutions of the associated homogeneous equation, and of course c1 c2 are arbitrary complex constant. But the question is how to find the solution u1 up. And before, if it was a full course, it means that we would have tried to see how one finds u1 u2 up using a method called a method of variation of constant. But the first thing is to find one solution of the homogeneous equation. And once one has knows one solution by guess or by whatever method, one solution, then the second solution can be found by a method called method of variation of constant. But how does it work? It means that we know, for example, for instance, one solution of the homogeneous equation, then we can write the second as a form u2x is u1x times a function hx that is to be determined. And to determine that, you have since u2 should be a solution, then one plug u2 in the equation, and then comes other auxiliary equation, and one solve it to find h of x. And usually one uses also something called the Wronskian, but of course it's not what I want to talk here, so I just mention it. And for the particular solution, it's the same again. One said that the particular solution upx is equal to u1x that we know times a function b of x, and this function b of x is to be determined as the same way we determine the first one by plugging in the equation and but now plugging in the non-homogeneous equation the form of up, that is u1 vx, and comes other set of equation that one solves to find v of x. Then a conclusion is that the method of variation of constant, a knowledge of one solution of a linear homogeneous equation of the second order is sufficient to find the most general solution of the inhomogeneous or non-homogeneous equation. And but the method of variation of constant cannot be easily generalized either to equation of higher order or to partial differential equation. And for this reason, the method of green function is introduced because it can solve problems where the method of variation of constant fails. Okay, this was summary of session 1. Now, summary of session 2. In session 2, if you do remember, I start reminding you about the direct delta function. That is an important mathematical object that is used in many problems in physics, and it's the form f of x is delta x minus x0, in the sense that delta x minus x0 is equal to 0 if x is different from 0, and it has other two properties that are written in this equation, just mentioned. And after that, I introduced last week what I call integral operator in this form of equation 6, that is a double integration, and the function k x second x prime is nothing than what we call the kernel of the operator, and I show you how we get the expression of the kernel. And the integral operator is completely continuous and Hermitian if the kernel satisfies two conditions that are in equation 7. And just to remind you what he said last week. And then after I mentioned the differential operator, that is the last point of last week. In fact, after I just add a certain two slide of properties that I missed to say, but one can read it from the notes. So a linear differential operator L is an operator in the function space whose action on vector U of this space is represented by this form that is in equation 8. Now, I have been asked the question by Kosi last week about the notation that we have here as a ket U, but this notation has been introduced by the direct in and called direct brackets, and here you have to see it as you can see a vector is just a notation that is there. We call this kind of, it's a ket, but it's seen exactly on the context here. I see it as a mathematical tool, as a vector, and they belong to the function space. So I added the preliminary note. I don't know if Kosi has seen that on the site, but yet what I define as ket bracket are in simple ways, in the sense that it's instead of writing vectors, we usually write in mathematics, we use this notation that's mathematically meaning is they are vectors, okay? But physically they means a state, but I don't go more than that. So a differential operator is then defined in that equation 8, and then for the notation I can have various notation that I just have here, like if I write Lx Ux, where Lx is also the operator associated to the operator L. Okay. And then the form of L of x does not determine uniquely the differential operator L, but the boundary condition prescribed are prescribed because one need to add boundary conditions that are part or partial of the definition of the operator L itself. And the function U of x, when you apply the differential operator L on U of x that represents, or that are the coefficient, as I said last week, of the vector U, abstract vector U on the domain of L, must be sufficiently differentiable and also satisfy the boundary conditions. And differential operators are in general not bounded. However, a differential operator L may have an inverse operator L minus 1, only bounded by completely continuous. And as you will see, a L minus 1, that's the inverse of the differential operator, is then an integral operator. Okay, that's why, and the most important differential operator with occur in physical problem are second order. That's why we are interested here in solving second order linear non-homogeneous differential equation or equation using the method of green function. So these are basically the summary of last week and 2 weeks ago. Now, let me start now with my board. Okay, Jamboard. I hope I found it. Oh, new shell. This is last week. Okay. I'll stop share. I have to do a new share. Let me find one. Okay. Okay, this is my screen. Okay, so today let me see. Okay, that too. Today then we are 19 October. And today is about green functions. So I will define green function. I will give the properties and also constructions. Okay, so it's today. So what is our problem now? We seek solution of second order. This is our problem we want to solve. We seek solutions of second order non-homogeneous ordinary differential equations using a method known as the method of Green's functions. Okay. So, okay, let's consider the following problem then. Find the solution of the non-homogeneous equation Lx ux is equal to f of x with boundary conditions B1 U is equal to alpha 1 UA plus beta 1 du dx x equal to A plus gamma 1 UB plus delta 1 du dx x equal B is equal to 0. And the second boundary condition on U is alpha 2 UA plus beta 2 du dx x equal A plus gamma 2 UB plus delta 2 du dx x equal B is equal to 0. Here we say that B1, B2 are homogeneous boundary conditions. So our problem is how to solve non-homogeneous second order linear equations with homogeneous boundary condition using the method of green function. So this is our problem today. So our problem is then equivalent to the following. Our problem is equivalent to the algebraic problem of finding solution of the operator equation L is the differential operator, U is the vector on the function space, is equal to F as a function, okay? Where, of course, L is defined by Lx together with the boundary condition. Let me write it well, boundary condition. That are B1U, B2U. So our problem is equivalent to this operator equations. So how do we solve that? Provided there exists an operator G satisfying Lj is equal to identity, where E is the identity operator, the solution of LU is equal to F is U G F. So if we can find to solve the operator equation L on vector U is equal to vector F, if provided we have an operator G that satisfies operator L times operator G is equal to E, where E is the identity operator, then the solution of LU is F is U equal GF. If the operator G exists, it is called Green operators. Okay. So, but what do we know? We know, as I defined last week, how to set a form of integral operator. We have also seen that for a differential operator, the inverse is an integral operator. So let us, in order to find G, our operator G, let's tentatively write G as an integral operator, since we know that the inverse of a differential operator will be an integral operator. So let us tentatively write G as an integral operator. So we write G as the form we wrote last week, integral AB, double integral dx prime, dx second, vector x prime, weight wx prime, g x prime, x second, that might be the kernel, omega x second, and bra x second. So let's tentatively see if this form would be what we're looking for. Now, if we have that, let's see the following. By the way we define the differential operator L, we have X, L, J, Y can be written as Lx, X, J, Y. There is a question C. No, I don't assume I have to answer to that. There is a question by Zagania, that if we assume questions, are we assuming LG equal GL equal E? This is the question. And the response is no. For the moment, I assume that if I have LG equal E, then I can find a solution. And you will see if I find a solution or if I construct G, G will be only the right inverse of L. I hope I answered to the question. Yeah, okay. So for the moment, I says no, I only have that at the right side. Okay, only this. Okay. So let's evaluate the what is x, j, y. Okay. If I replace j by its expression, it will be integral AB dx prime dx second x prime omega x prime g x prime x second omega x second y. Okay. But what do we know? We know that from last week that this can be written as these are not a good normalization condition, that's one, but is rather delta x minus x prime divided by omega x prime. And this is delta x minus x second divided by omega x second. Okay, with respect to that, I can rewrite like that. It is double integration dx prime dx second. I replace delta x prime omega x prime, so cancel omega x prime. So I will have here delta x minus x prime g x prime x second delta x minus x second. Sorry. Okay. No, I'm sorry. Delta x second minus y. Just right. I correct you. I'm sorry. X second minus y, then x second minus y. Okay, but since I have this, I will see how I arrange this double integration to make it see well. So what do we have? We have that x g y is integral ab dx prime omega. Now we simplify the omega x prime delta x minus x prime integral a b dx second g x prime x second delta x second minus y. But what is this integration if we use the delta distribution property? This is nothing than g x prime y, because we integrate over x second of g x prime x second delta x second minus y. And then this remain integral ab dx prime delta x minus x prime g x prime y. And again, if we use the fact that we have the property function distribution, then this become g x y. So this is nothing x j with the form of the operator j that we have y. This gives me j of xy. So I am back. We were x LJ Y is LX X J Y, okay, and this is equal to, as we have seen, LX J X Y. But yet we know that this is, I assume that this is equal to E. If this is E, so I can also say that this is equal to X, Y. But what is equal first to X? Let's replace first E, Y, and this is X, Y, but this is yet delta X minus X. So what have we shown here? We have shown here that I have LX, operator LX. My operator equation is also equivalent to LX G XY is delta X minus Y divided by omega X. Okay, so, and in that sense now, I say that therefore the kernel, because GXY is the kernel of the operator G, the kernel GXY of the operator G satisfies LX GXY is delta X minus Y divided by omega X. And what does it mean? This means that we have two conditions. We have two things that we can say. It means that if I have LX GXY is equal to delta X minus Y omega X, that means that LGXY is equal to 0 for X different than Y. Okay, and also I can say that it means that G of X that means that GXY satisfies the homogeneous equation anytime that X is different than Y. So it's just that LX JXY is equal to delta X minus Y omega X satisfies the same equation as UX, in the sense that I solve LX UX is equal f of X, except that the non-homogeneous term f of x has been replaced by delta x minus y omega x, okay? And a gxy as a function of x must satisfy the same homogeneous boundary conditions as those imposed on ux. So the function xy depend on two variables x and y, but why we consider the variable x is because if in the expression of x L G y, this expression is meaningful when G y belongs to the domain of L. So what do we know now? We know that except at x equal y, gx, the function gxy satisfy the homogeneous equation. And we know that as a function of x, it must satisfy the same homogeneous boundary condition as u. These are two information we have yet with respect to our green function. And then what can we say right now? Whenever a solution of LXG XY is equal to delta x minus y omega x exists, the integral operator is G is well defined and is the right inverse of the differential operator L. So this is about the question someone has asked me. So that's why in our assumption is only at the right side that we have the equality to the equality of the unit operators. Now, what are the properties of G? For an emission, first property is the following. We have G x y is J y x conjugate, okay, for emission operator L. Okay. And in addition, if the coefficient of L of X, if the coefficient of Lx are real, Jxy is symmetric. Then symmetric. Okay. Second property that I don't show, but that is true, is that Jxy is continuous at x equal y. Okay. Third condition, properties, not condition, third properties is that now since J depend on two variables x and y, if I mention J derivative, then I take the partial derivative. So the partial derivative of J respect to x is discontinuous at x equal y, and the jump of t at y is given by the limit when x goes to y, x greater than y, of j partial derivative j with respect to x minus the limit when x goes to y, x smaller than y, of partial derivative j xy respect to x is equal to 1 over the weight at point y. A is the coefficient of the second order derivative with respect to x. So these are three properties of the green function that I state here, but that I don't demonstrate, because the demonstration of those three properties can be the whole mini course, but you can find the demonstration in the book of Dennery that I mentioned as a reference. Now, how do we proceed concretely now to construct green function? This is what I want to do, and I have a kind of 15 minutes. Okay, go to that. How do we proceed concretely? This is the question. Now, to do that, let's say we want to solve ax d square u dx square, you can put u of x here, plus bx dux dx plus cx ux is f of x, where x is, we take an interval a, b, and of course a of x different from 0. I assume that the coefficients are real, not complex. And then we have a homogeneous boundary condition, b1u is equal to 0, b2 b2u is equal to 0, and that is homogeneous boundary conditions. Here, of course, a first thing to check is here, what do I call Lx here? So here Lx is Ax, the operator. No, it's an operator. d square dx square plus bx dx plus cx. This is what I will call L of x if I have this form. And of course, I still assume that b1, b2 is 0. And the homogeneous equation associated is ax d square u x dx square plus bx du x dx plus cx ux is equal to 0. So this is what I call the homogeneous equation when I set f is 0. Now let's assume j, or suppose jxy is the associated green functions. If I suppose that a gxy is the green function, what does it mean immediately with respect to what we have said previously? It means that I will have Lx j xy is equal to delta x minus y omega x. And that means that I have Lx jxy is equal to 0 for x different on y of y. And that means, and what does it mean? It means that Lj except x equal y, j xy satisfies the homogeneous equation on AB, where I took y. This is the point. And if it satisfies the homogeneous equation and together with the homogeneous boundary condition, concretely it means that I have ax d squared, but here I do partial derivative because g depends on two variables x and y, xy with respect to x plus bx d j xy with respect to x plus c of x g xy is equal to 0 for, of course, x different than y. And it does satisfy also jxy satisfy the boundary condition that b1 j is equal to 0 and second b2 j is equal to 0. So if I suppose that there is an associated green function associated to the differential equation that we have, so it means now what I just written, that jxy satisfy the homogeneous equation whenever x is different than y and satisfy the boundary condition with respect to the variable x. Now we know that for homogeneous equation, the solution of any solution of the homogeneous equation is a linear combination of the fundamental set of solutions. So now if we suppose u1x, u2x are a fundamental set of solutions, of the homogeneous equation, then we can express the most general solution of Lx j x y is equal to 0 only valid on the interval AB to the left and to the right at the point x equal y. So what does it mean? If I have my interval AB like that, I have, for instance, y here. So I know that if I am here, Jxy satisfy the homogeneous equation. So I can write that Jxy, if satisfy the homogeneous equation and if there is fundamental set of solution, will be a kind of C1 U1x plus C2 U2x, since it should be a linear combination of a fundamental set of solution for a x between a and y, and of course x should not be equal to y. And I know that except the point y, if I'm this size, then Jxy satisfies the fundamental, the homogeneous equation. Then I can say that on this part of the interval, I have xy is equal to d1 u1x plus d2 u2x for y smaller than x that can be equal to b. And of course, where C1, C2, D1, D2 are arbitrary constants that may depend on y, because C1, C2, D1, D2 may depend on y, because I have Gxy that is a function of x and y, but u depend on x, okay? That may depend on y. Okay, so what do I mean now exactly? I mean exactly that, okay, I have 5 minutes. I mean exactly that if Jxy satisfy the homogeneous equation for x different than y, I can safely write that Jxy is equal to C1 that can depend, a constant that may depend on y, U1 of x, that is one of a fundamental set of solution, plus C2, that is a constant that may depend on y, times U2 x, that is the second fundamental set of solution on the interval x, y. And then I can have also on the other part of the interval with at the right side of y, D1 that can depend on y, U1x plus D2 U2x if I'm y x b. So the only problem is y, but at y we know that there is it's continuous, so we'll use now we have to determine, let's determine C1, C2, D1, D2. If we know C1, C2, D1, D2, then we know U1 of X, U2 of X that are this fundamental set of solutions. Then we have our green function that is constructed. But in order to have that, what do we have to use? We have to use the property and all information we know about the green function. We know that the green function satisfies the same homogeneous boundary condition with respect to the variable X. Then we have to check that if we have concretely, then one check that B boundary condition 1 at JXY should be equal to 0. And we have to do with respect to each interval. Okay. So a second boundary condition at JXY, but regarding the variable X should be equal to 0. So these two conditions may give us already some information on the constant to be determined. The second property that can be well used is that JXY must be continuous at X equal Y. What does it mean concretely? It means that the limit when X goes to Y, but X smaller than Y, of JXY should be equal to the limit when X goes to Y, X greater than Y, of JXY. And if you want to concretely do that, then we look at if we do the limit when X goes to Y with respect and X smaller than Y, we have to see the left side of the equation, or what can we use the expression there, and the other side doing the limit when X goes to Y, X greater than Y, we have to see the right side of the equation of the interval, and then we check that, and then we equalize, we do the equality, and when one do the equality, it give us a condition on C1, C2, D1, D2, and the third property should be also used, and that is the limit, because there is a discontinuity of the first derivative of G with respect to Y at the point X equal Y. Then limit when X goes to Y, X greater than Y, of partial derivative X of J XY with respect to X, minus the limit when X goes to Y, X smaller than Y, of partial derivative JXY with respect to X should be equal to 1 over the weight at Y and A at Y. And usually one takes the weight function equal to 1 if they don't give us specifically. So these three conditions imposed on JXY determined the four constants C1, C2, D1, D2, and hence the green function this is the point. So this is how one constructs the green function, because the green function satisfies the homogeneous equation x together with the same boundary condition with respect to x whenever x is different than y. So if you consider the interval AB and we take off the point y, so at each part of the interval with respect to y, the green function satisfies the homogeneous equation. It means it can be written as linear combination of the set of fundamental solution of the homogeneous equation. And once we set that with constant, we use now the property that we know about the green function to determine the constant. So once we have that, the solution is this, and this is the last thing I says now. Once we have the green functions J, X, Y, the solution of the problem Lx Ux is equal to f of x on the interval AB, with boundary conditions that are homogeneous, is Ux is integral AB dy, the weight, J x y, f of y. So this is the solution, but then if you can get it because we already says everything, the apparatus equation is this, provided J exists, if J exists, in the sense that provided I will have Lj is equal to E, then I have the solution U is JF. But if you remember my last week lesson, if I do that, this give me X J F, and last week we have done that. This is nothing than U of X, and this is nothing than the integral AB dy omega y J x y f of y. So I'm done here. I stop here. Okay.
Yeah, thank you very much, Laura. It was again a very nice lecture. Thank you so much. Really much appreciated.